Okay, the problem we're going to talk about involves doing a crunch on a ab machine. So, of course, we're seated at the machine, but elbows resting on a pad, upper body lowers, what I said was 30 centimeters, upper body with a mass of 60 kilograms in the crunch motion. And then the force exerted through a total of 60 centimeters. I think the 30 centimeters is probably a little high, the 30 kilograms may be a little high. The 0.6 meters may be a little high, but that's okay. We're going to just take this as the correct information. So, in the descent during the crunch exercise, my potential energy decreases because I have at least 30 kilograms of my mass is descending 0.3 of a meter. And that comes out to a negative 90 joule change in potential energy. I do work. Okay, the work I do, I'm exerting a force of 500 newtons through 0.6 of a meter. That's 300 joules of work. Now, I got messed up in this problem, and the mess up is still there. I did have the error that I call this 150 joules because I was using 0.3 meters there. I didn't look carefully enough at the problem when I did it in the class. So I have corrected the 150 to make it 300 joules. So this is probably a little more realistic. Again, these estimates are probably a little high. How much work is done by the net force acting on the weight machine? Okay, well, the work done by the net force on the weight machine is 0 because I start the crunch stationary, I end the crunch stationary. And of course, here where it said equal the change of potential energy of the stack, that can't be equal to the work done by the net force on the system because the work done by the net force on the system is equal to the change in kinetic energy. So I'm not even going to try to explain what I was thinking or failed to think when I wrote this down. I was obviously not thinking very clearly at that time. So this should be equal to the change in kinetic energy, which is 0. Okay? Now, the net gravitational work on the system is what? Well, it consists of the work gravity does. Well, let me pause for a second. I just realized there's still a problem with what I'm saying here, but I'm going to go on. It's a fairly minor problem, and we'll address it after I complete this. Okay, so the work done by gravity on the system is equal to what? It's equal to the 90 joules that gravity does on the system as the potential energy decreases, as the potential energy of the upper part of my body decreases by 90 joules. Now the problem there is that, as I just stated, I'm not part of the system, but we'll resolve that in a minute. Hopefully satisfactory. Okay, so the 90 joules is the work done by gravity, again, on my mass as I descend. The other part of the work done by gravity is the work done on the stack. So this is going to be, let me use a different color so we don't confuse anything. That's the work done by gravity on me, plus the work done by gravity on the stack. And the work done by gravity on the stack is equal and opposite to the change in the potential energy of the stack. So that where I have had the equal change in potential energy up here, which is really pretty nonsensical, we have the negative of the change in potential energy of the stack. That's the work done by gravity on the stack. Now, this might be a little hard to read. The board is a little rough. And I'm not getting real good impressions with the chalk. So the work done by gravity on the system then is the 90 joules on my mass, although I'm not part of the system right now, I will be in a minute, minus the change in potential energy of the stack. And that's going to be equal to 0. I guess I can stick in an equal 0 there. And we then conclude that the change in potential energy of the stack is 390 joules. And that makes sense because I'm doing 300 joules of work with my muscles, such as they are, and gravity's doing 90 joules of work to lower the 30 kilograms of my mass. The system is the 30 kilograms of my upper body plus the machine. Okay, so we'll resolve that. I said earlier that the system would be just the machine. I'm going to say the system is the 30 kilograms of my upper body plus the machine, so that the 90 joules that gravity does, 90 joules of work that gravity does on my upper body is done now on the system. And, you know, you don't, I talked about, you know, seeing, you know, slicing somebody at the upper body and weighing it to estimate if that's really 30 kilograms. Of course, you wouldn't want to do that with a live person. But there are other ways to make those estimates. And in a sense, I'm kind of dismembering myself here, taking the 30 kilograms of my upper body and separating them from the muscles that do most of the work here. Excuse me. Okay, that's legitimate, even if the muscles do extend a little ways into my upper body. The muscular action plus the effect of gravity opposes the stack. So there's the resolution, at least one resolution of the situation. My motivation for this problem was I had an injury, and I was needed to do the crunches. Didn't want my abs to go all to heck, at least any further than they already are, while I healed the injury. And I dropped down to about 60% of the weight on the machine, and it felt really like I was hardly doing anything. Even though after doing a whole lot of repetitions, I did end up getting just a little bit sore from a much lighter weight, and a weight that felt like it was almost nothing. Why did the weight feel so light? Well, in the first place, your perception of weight increases rapidly as you get close to your limit. So if you drop 40% off of something that's close to your limit, you really doesn't feel very heavy at all. But the other thing is simply that my upper body was contributing to the force I was able to exert. And the the question arose, just how much was it contributing? So I came up with this model, and again, not a very realistic model. And the weights here are closer to the weights that I normally use than to the weights I used at the 60% reduction. But we still see that there's a significant likelihood that the work I do, the work done by gravity, is a significant percent of the actual work that I do. Then we could, of course, ask what happens when I return to my starting position. I'm not doing any work. The stack is lowering, and the machine is doing work on me. Did I somehow contribute to that energy, or it's pretty clear that the only energy I'm really contributing is the muscular action that does this 300 joules of work. Now we can actually work friction into the system, because there is some friction in this system, and it would be possible to measure the friction by going to the machine and measuring the force required when you're pushing the machine, when you're pushing the bar down so that the weight stack is raising, and then when you return. There'll be a difference in the force, and that would be the difference due to the friction. Now, I'm not going to completely work out the other questions, but I will indicate that if the displacement of the stack, again, not getting very good, the writing is a little grainy at this height, at this size, so I don't know how readable this is, but this just says if the delta S of the stack is 0.8 meters, then the weight, well, gravity is going to do 390 joules of work on the stack against its motion, but the weight is going to then be the 390 joules of work done divided by the 0.8 meters of the displacement, and that's going to be a little under 490 joules, 490 newtons. And then how much of that is done due to the action of my abdominal muscles? Well, or whatever set of muscles I use, because I use some muscles around my shoulders as well, just because of the configuration of the machine. Well, 90 of the 390 joules of work that I do is done by gravity on that 30 kilograms of upper body mass. So that 300 of the 390 joules of work are actually done by my abdominals. So 390ths, which would be 10/13ths of the work, of the weight, is actually raised by the action of my muscles. The rest just by the fact that I'm flopping over on top of the machine, and gravity is contributing that.